All right, let's talk about a word that most people's eyes glaze over, subnetting. But what if I told you that behind all those intimidating numbers and dots, there's a logic so simple it's actually kind of beautiful? Well, today we're going to pull back the curtain and demystify the whole thing.
Welcome to Super Courseva. Unlock the secrets of the internet and master computer networking. Let's dive in.
So let's kick things off with a little mystery. You've seen a million IP addresses, right? But have you ever stopped to think why you never ever see a number like 301 or 500 or 999? There's a reason for that, and the answer gets to the very core of how computers will think. Okay, I'm going to say a word. Binary. Now, if you just physically recoiled, hey, you are not alone. There's this huge myth that binary is some kind of scary high-level math, but we are about to bust that myth wide open. It's not hard, it's just a different way of counting. So our first clue on this journey is realizing that computers don't use complicated math to count. In fact, the system they use is way, way simpler than the one we use every single day. Let's see what that looks like. It all comes down to what you have to work with. For us humans, we've got 10 fingers. So naturally, we developed a system with 10 symbols, 0 through 9. We call it decimal. But computers, they just have tiny little switches that are either on or off. So their system only needs 2 symbols, a 1 for on and a 0 for off. That's it. That's literally all binary is. And to really wrap your head around how this works, you don't need a fancy calculator. Nope. All you need to do is think about the odometer in a car. This simple little analogy, it's the key that's going to unlock this whole concept for us. Okay, so picture it. Your car's odometer clicks up, 0, 1, 2, all the way to 9. And then what happens? It's run out of symbols, so it does a little trick. It flips that first column back to 0, and it rolls a 1 over into the next column. Bam, you've got 10. We see it all the time, but we don't really think about that simple rule. Now, computers do the exact same thing. They just run out of road a lot faster. They count 0, then 1, and boom, out of symbols. So what do? They follow the exact same odometer rule. Reset the first column to 0 and add a 1 to the column on the left. And that, right there, is why 10 in binary actually means the number 2. It's the same logic. And you can see the pattern building here, can't you? 0 is 0. 1 is 1. 1, 0 is 2. 1, 1 is 3. Uh-oh, out of symbols again. So reset and carry the 1. 1, 0, 0 becomes 4. It's the same simple odometer logic, just with fewer digits to play with. Okay, so we've cracked how computers count. Now let's connect that back to our original IP address mystery. It all comes down to one single magic number. The total number of things a computer can represent boils down to this incredibly simple formula, 2 to the power of the number of bits it's using. And remember, a bit is just one of those binary digits, a single 0 or a 1. Now, in an IP address, each of those 4 sections is called an octet. That's just a fancy networking word that means it's made up of 8 bits. So we just plug 8 into our little formula, which gives us 2 to the power of 8. And the answer is 256. That's it. With 8 bits, 8 of those on-off switches, a computer can create exactly 256 unique patterns. But here's the key. Computers always start counting from 0. So those 256 possible values aren't 1 to 256, they're 0 all the way up to 255. And that's the ceiling. That's the highest it can go. And that is why you will never, ever see a 300 in an IP address. The system simply can't count that high with only 8 bits. Mystery solved. All right, we've figured out how computers count. Pretty cool. Now, for the final piece of the subnetting puzzle, we need to see how they make simple decisions. And it all comes down to these little things called logic gates. So this is where things get really interesting. We're not just counting anymore. Now our 1s and 0s take on a new meaning. 1 means true and 0 means false. And computers use these dead simple rules to compare them. Let's look at 2 of the big ones. First, you've got the OR operator. Think of OR as the ultimate optimist. As long as either of its inputs is true, it says, yep, success, the result is true. But then you have the AND operator. AND is a total perfectionist. It looks at its 2 inputs and says, are both of you true? If even one is false, the whole thing fails. And for our puzzle today, this little perfectionist is the star of the show. So here's how our perfectionist brain works. False and false, that's a false. False and true, nope, still false. The only way the AND operator gives you a true or a 1 is if both inputs are true. It's all or nothing. Okay, this is it, the grand reveal. We've learned how to count like a computer, we've found our magic number, and we've met our perfectionist AND operator. It is time to put all three of these clues together and finally solve the subnetting puzzle once and for all. So, to figure out what network you're on, your router only needs to look at two things: your device's unique IP address and this other number that travels with it called the subnet mask. And here's the ridiculously simple three-step process it follows in a fraction of a second. First, it converts both the IP address and the subnet mask into binary. Then, it lines them up and applies that perfectionist AND rule to every single pair of bits, straight down the line. The number that pops out at the end, that's the network ID. Now, here's the real magic. A subnet mask is basically just a string of ones followed by a string of zeros. Think of it like a filter or a stencil. Wherever the mask has a 1, it lets the bit from your IP address pass through. But wherever the mask has a 0, it blocks the IP bit and just puts a 0 instead. It keeps the part that identifies the network, and it completely erases the part that identifies your specific device. And that's the whole secret. Your router does this quick little calculation for your computer and for the computer you're trying to talk to. If the network IDs at the end are a perfect match, the router knows you're on the same local network, the same street basically, and it connects you directly. If they don't match, it knows it needs to send your data out to the bigger internet to find its destination. So what seems like this mind-bendingly complex system is actually just simple counting and one single perfectionist rule applied over and over at lightning speed. It really makes you wonder, doesn't it? What other complex technology that we use every day is actually just a few incredibly simple rules stacked on top of each other?